In this podcast, we'll find the main properties of a rational function and use it to help us graph. One helpful thing to do whenever you see a rational function is to factor it completely. For the numerator, we can factor out the leading coefficient of x squared and rewrite it as negative 4 times the quantity x squared minus 1. Since x squared minus 1 is the difference of perfect squares, we can factor that further into negative 4 times x minus 1 times x plus 1. The denominator is a quadratic. The product should be negative 6 for the factors, and the sum is positive 1. So x plus 3 times x minus 2 should factor the denominator completely. Now that we have it completely factored, now we can look for the properties. We always check for wholes first. Wholes occur when we have the same factor in the numerator and denominator. In this case, all of these factors are different, so we have no hole in this graph. Zeros occur when the numerator is equal to 0. Again, a fraction is 0 if the numerator is equal to 0. So in our numerator, we have zeros at when x is equal to 1 and when x is equal to negative 1. Again, since each of these factors were with exponent 1 power 1, we have them each with multiplicity 1. Vertical asymptotes are where the function's undefined. Again, a fraction's undefined where the denominator is equal to 0. So we have two vertical asymptotes for this graph at negative 3 and at positive 2. As for the end behavior, our function will either have a horizontal asymptote or a slant asymptote. One way to look quickly and check to see which one it is to look at the degrees of the largest degree term. If the degrees are equal, we'll have a horizontal asymptote. When the degree of the numerator term is one more than the degree of the denominator term, that's when we'd have a slant asymptote. In this case, since they're equal, we do not have a slant asymptote, but we have a horizontal asymptote. There's different ways you can find a horizontal asymptote. You can divide by basically the highest power of x squared, divide it into all the terms, and look and see what happens when x is really big. Or you can use the fact when the degrees are the same, it's going to end up being the ratio of the coefficients. So it's negative 4 over 1. We should have a horizontal asymptote at negative 4. We now want to put all this information into our graph and use it to help us sketch what this function looks like. So drawing in the horizontal asymptote, again, the ends of our graph should get closer and closer to negative 4. Sometimes it's helpful to only draw the horizontal asymptote on the very ends because it reminds you the function could cross the horizontal asymptote in the middle. It just approaches this horizontal line on the very far left and far right. Next, we can add some vertical asymptotes. These are places where the function can't cross. So at negative 3, and we had it at positive 2. We can add in our zeros, which basically give us x-intercepts at positive 1 and negative 1. And we know from our function, each of them had multiplicity 1, so our function should be crossing the x-axis in those spots. Now we can use this to draw most of our graph, and if we need help, we can add a couple more points to the graph to help us see what it looks like. One thing we'll notice is from the horizontal and the vertical asymptotes, if the function has to go close to negative 4 to the far right, and it has to be approaching this vertical line, well, we know for starters, it has to look something like this on the far right. It has to be approaching the horizontal asymptote, and the reason it can't go up from here is, well, that would cause a new root to appear, a new 0 or x-intercept to appear, and we know the only x-intercepts are at 1 and negative 1. Same idea, the left side of our graph has to be in the same type of fashion. It couldn't go up from the horizontal asymptote because, again, then we'd have an additional x-intercept, which we shouldn't have for this graph. To see what happens in the middle here, it might be helpful to add one more point to this graph. One nice easy point to look at is the y-intercept. We can find that by plugging in 0 into our function. When we plug 0 into the function, the top should go to 4, the bottom should go to -6. So we have the point -2/3 for y when x is 0, somewhere about here. Using this, we can now connect to draw the rest of our graph. We know that the function has to pass through this point. It must get close to the x-intercept at 1, and we know it crosses there, and it has to go up towards this vertical asymptote. Again, it couldn't turn around and come back down because there's no additional x-intercepts. Same idea, if we're connecting this, it should eventually go from the y-intercept, the point 0, -2/3, to this x-intercept to the left at -1. It has to cross there, and it would have to go up towards the vertical asymptote there. So the overall properties of our function showing the correct 0, vertical asymptote, and end behavior should look something like this.